Hey everyone, welcome back to Incognito Engineer. In this video, we will break down Apache Spark step by step, starting from the basics and slowly building up to how Apache Spark works internally, all in a way that any beginner can understand. So let's get started. Before we dive into Apache Spark, let's do a quick recap of Hadoop because Spark was created to solve some of Hadoop's limitations. Hadoop mainly consists of three core components. First, HDFS, or Hadoop Distributed File System. HDFS is responsible for distributed storage, allowing large files to be stored reliably across multiple machines. Second, we have MapReduce. MapReduce is Hadoop's batch processing engine. It processes data by breaking jobs into maps and reduce tasks, but it relies heavily on reading and writing data to disk. Third, we have Yarn, which stands for Yet Another Resource Negotiator. Yarn handles resource management, deciding how much CPU and memory each job gets in the cluster. Although Hadoop was revolutionary, it has some core limitations. MapReduce is disk-based and slow because data is written to disk after every step. It is also mainly designed for batch processing, making it unsuitable for real-time and interactive workloads. These limitations are exactly why Apache Spark was introduced. Now that we understand Hadoop's limitation, let's see why Apache Spark was created. The first reason is speed. Spark is much faster than MapReduce because it avoids unnecessary disk operations. This leads to the second reason in memory processing. Spark keeps data in RAM whenever possible, which makes repeated operation much faster. The third reason is real-time analytics. Unlike MapReduce, Spark can process streaming data in real time. Finally, Spark efficiently handles iterative workloads, which are very common in machine learning and data analysis. Together, these features make Spark a faster and more flexible alternative to traditional big data processing systems. Now let's clearly define what Apache Spark is. Apache Spark is an open source, distributed data processing engine. This means Spark distributes computation across multiple machines instead of relying on a single system. Spark is designed for big data analytics, where datasets are too large to be processed efficiently on one machine. One of Spark's most important ideas is processing data in memory instead of constantly writing to disk. Spark also runs on clusters, which are a group of machines working together in parallel. So the key idea behind Spark is simple but powerful. Keep data in memory to speed up computation. Now that we know what Spark is, let's see where Spark fits in the big data ecosystem. Think of the big data stack as layers. At the bottom we have HDFS, which handles storage. Above that we have Yarn, which manages cluster resources and jobs. On top of Yarn is the processing layer. Earlier, this role was handled by MapReduce. Today, Spark is commonly used instead because it's faster and more flexible. So Spark does not replace Hadoop completely. It mainly replaces MapReduce while still working with HDFS and Yarn. Let's look at the key feature of Apache Spark. First, high-speed throwing memory processing. Easy to use API. Spark supports Python, Scala, Java, and R. Third is fault tolerance. If a task fails, Spark can recover without restarting the entire job. Scalability. Spark can scale from one machine to thousands. Finally, Spark is a unified analytics engine supporting SQL, streaming, machine learning, and graph processing. Apache Spark is a collection of libraries built on a common engine. At the center is Spark core, which handles scheduling, memory management, and fault tolerance. Spark SQL allows working with structured data using SQL and DataFrames. Structured streaming enables real-time data processing. MLlib provides machine learning algorithms. GraphX is used for graph and network processing. All these components share the same execution engine. Now let's understand Spark architecture. At the top is the driver, which runs the main program, creates the Spark context, builds the DAG, and schedule works. Below the driver is the cluster manager, such as Yarn, which allocates CPU and memory and launch executors. At the bottoms are the executors. Executors run tasks, store data in memory, and execute work in parallel. Spark reads input data from a storage system like HDFS or S3, processes it in memory, and writes result back. Let's see how a Spark application runs. First, the application is submitted using Spark Submit. Second, the driver starts and coordinates execution. Third, when an action is called, Spark builds a tag, split the job into stages, and further into tasks. These tasks are sent to executors which run them in parallel. Key insight here is only tasks run on executors and execution starts only when an action is called. We will see later what an action is. Now let's clearly understand jobs, stages, and tasks, because this is how Spark actually breaks down your program internally. In Spark, everything starts with an action. When an action like count, show, or save is called, Spark creates a job. You can think of a job as the entire work Spark needs to do for that action. Each job is divided into stages. A stage represents a group of operations that can be executed together without shuffling data. Whenever a Spark needs to move data across executors, for example, during a group by or join, it creates a new stage. Each stage is further divided into tasks. A task is the smallest unit of work in Spark. Each task processes one partition of data, and tasks are what actually run on executors. So to summarize, one action creates one job. A job is split into multiple stages. Each stage consists of many tasks. So understanding this hierarchy helps you understand Spark performance and execution behavior. One important thing to remember is that shuffling data creates new stages, and shuffles are expensive because they involve network communication. One of Spark's most important concepts is lazy evaluation. Transformations like map, filter, and group by are not executed immediately. Spark simply records them and builds an execution plan. Execution starts only when an action like count or save is called. This allows Spark to optimize the entire workflow before running it. The execution plan Spark builds is called DAG, Directed Acyclic Graph. The DAG represents the sequence of operations and their dependencies. Spark uses the DAGs to optimize execution, understand dependencies, recover from failures by rerunning only failed tasks. You can think of the DAG as Spark roadmap. Now let's take a deeper look at RDD and partitions because this explains how Spark actually processes data in parallel. RDD stands for Resilient Distributed Dataset. An RDD is an immutable distributed collection of data. Immutable means once an RDD is created, it cannot be changed. Distributed means the data is spread across multiple machines in the cluster. Another important feature of RDD is fault tolerance. Spark tracks how an RDD was created using something called lineage. So if part of the data is lost, Spark can recompute it automatically. Now the most important concept here is partitions. When Spark creates an RDD, it splits the data into multiple partitions. You can think of each partition as a chunk of the dataset. These partitions are the reason Spark can process data in parallel. Now let's see how Spark processes these partitions. Spark follows a simple rule. One task processes exactly one partition at a time. When an action is triggered, Spark creates tasks and each task works on a single partition of the RDD. These tasks are then sent to executors. Executor runs tasks in parallel across the cluster, which is how Spark achieves high performance. So the full flow looks like this. We have an RDD. From RDD we get partitions. From partitions we run tasks. And These tasks are run on executors. Finally, the key insight you should remember: the number of partitions control parallelism in Spark. More partitions usually allow more parallel processing, but too many partitions can also add overhead. Understanding RDD and partition make it easier to understand Spark execution model and performance behavior. Now that we understand RDDs in detail, let's look at the other data abstraction provided by Spark. In Apache Spark, RDD, data frame, and datasets are all data abstraction. A data abstraction is simply a way to represent and work with distributed data without worrying about low-level execution details like task scheduling or fault recovery. Let's start with RDD. RDD are the lowest level abstraction in Spark. They give you a lot of control, but they require more manual work and optimization. To make Spark easier and more efficient to use, Spark introduced DataFrame and datasets. DataFrame and datasets are higher level abstractions compared to RDD. They hide many low level details and allow Spark to automatically optimize execution. A data frame represents data in tabular format similar to a table with rows and columns like Excel sheet or database table. This makes it very easy to work with structured data and SQL-style queries. A dataset is similar to a data frame, but it also provides type safety, which is mainly useful in Scala and Java. Even though these abstractions looks different, they all run on the same Spark execution engine. Under the hood, Spark still uses concepts like tag, stages, task, and executor to process the data. The key takeaway here is simple: RDDs are low-level abstraction, while data frame and datasets are higher-level abstractions that make Spark easier, safer, and faster to use. That's why in practice, beginners should start with data frame and use RDD only when low-level control is required. One point to remember here is that operational RDDs are divided into two types of tasks: transformations like map and filter, actions like count and collect. Now let's do a quick comparison between RDD, data frame, and datasets using this table. RDD provide medium performance because Spark cannot optimize them automatically. Data frame and dataset provide high performance because Spark can apply internal optimizations. RDD have low ease of use since they require more low-level coding. Data frames are very easy to use, especially for beginners and people familiar with SQL. Datasets fall somewhere in between, offering type safety but slightly more complexity. RDD require manual optimization by the developer. Data frames and datasets are automatically optimized by Spark using internal engines. So the overall recommendation is simple and practical: use data frame unless there is a specific requirement to use RDDs or dataset. This approach will give you better performance and smooth learning. Now let's talk about where Apache Spark is commonly used, along with common beginner mistakes and important limitations you should be aware of. Let's start with common Spark use case. Apache Spark is widely used in ETL pipelines where large volumes of data are extracted, transformed, and loaded efficiently. Spark is also heavily used in machine learning, especially when working with large datasets and iterative algorithms. Another popular use case is streaming analytics, where Spark processes real-time data such as logs, events, or messages. Spark is commonly used for log processing, where massive log files need to be analyzed quickly. Finally, Spark supports interactive SQL, allowing analysts to run fast queries on big datasets. Now let's look at common beginner mistakes when working with Spark. One very common mistake is using collect on large datasets. This tries to bring all the data to the driver, which can easily crash your application. Another mistake is not caching reused data. If the same dataset is used multiple times, failing to cache it can lead to unnecessary recomputation. Beginners also often create too many small files, which hurts performance. And finally, many people ignore partitions, even though proper partitioning is crucial for Spark performance. Next, let's talk about when not to use Spark. Spark is not a good choice for small dataset where simpler tools would be faster and easier. It is also not ideal for simple scripts that don't require distributed processing. And Spark may struggle on memory-limited systems since it relies heavily on in-memory processing. Finally, let's discuss Spark limitations. Spark can have high memory usage, especially for large workloads. It often requires tuning to achieve optimal performance, and debugging Spark applications can be complex, especially in distributed environments. So, understanding these use cases, mistakes, and limitations will help you use Spark more effectively in real-world applications. Now let's put everything together and understand how Apache Spark works from start to end. Step 1. In most real-world systems, data is stored in distributed storage systems like HDFS or S3. Spark does not store data permanently. It reads data from these systems when needed. Step 2. When a Spark application starts processing data, Spark loads the required data into memory whenever possible. This is the key reason why Spark is so fast compared to disk-based systems. Step 3. Operations like map, filter, and group by are applied, but no execution happened yet. Spark only records these operations and builds an optimized execution plan. Step 4. When an action like count, show, or save is called, Spark finally starts executing the job. At this point, Spark builds the tag, split the job into stages and tasks, execute tasks in parallel on executors. In step 5, the final result is either written back to storage or displayed to the user. The most important key insight here is move computation to the data and keep data in memory whenever possible. This design principle is what makes Apache Spark fast, scalable, and efficient for big data processing. And here are some key concepts to remember, which is like a summary of the whole video. So some key points for DAG, job, stage, task, execution flow, and some important clarifications which you can review. Let's wrap up everything we have learned in this video. Apache Spark is a powerful big data processing engine designed to handle large-scale data efficiently. Spark is much faster than MapReduce because it processes data in memory and optimizes execution automatically. It is ideal for batch processing, streaming analytics, and machine learning workloads, all within a single unified platform. Spark is also best used alongside Hadoop, where Hadoop provides storage and resource management, and Spark handles fast data processing. To conclude, if this video helped you understand Apache Spark better, please like, subscribe, and share it with others who are learning big data. Thanks for watching, and see you in the next video.